Okay, so this is the first lecture on eigenvalues and eigenvectors, and that's a big subject that will take up most of the rest of the course. Again, matrices are square, and we're looking now for some special numbers, the eigenvalues, and some special vectors, the eigenvectors. And so this lecture is mostly about what are these numbers, and then the other lectures are how do we use them? Why do we want them? Okay, so what's an eigenvector? Maybe I'll start with eigenvector. What's an eigenvector? So I have a matrix A. Okay. What does a matrix do? It acts on vectors. It multiplies vectors x. So the way that matrix A acts is in goes a vector x and out comes a vector ax. It's like a function. With a function in calculus, in goes a number x, out comes f of x. Here in linear algebra, we're up in more dimensions. In goes a vector x, out comes a vector ax. And the vectors I'm specially interested in are the ones that come out in the same direction that they went in. That won't be typical. Most vectors, ax is in points in some different direction. But there are certain vectors where ax comes out parallel to x. And those are the eigenvectors. So ax parallel to x. Those are the eigenvectors. And what do I mean by parallel? Oh, much easier to just state it in an equation. Ax is some multiple, and everybody calls that multiple lambda, of x. That's our big equation. We look for special vectors, and remember, most vectors won't be eigenvectors, that for which ax is in the same direction as x, and by same direction I allow it to be the very opposite direction. I allow lambda to be negative or 0. Well, I guess we've met the eigenvectors that have eigenvalue 0. Those are in the same direction, but they're in a kind of very special way. So this is the eigenvector x. Lambda, whatever this multiplying factor is, whether it's 6 or minus 6 or 0, or even some imaginary number, that's the eigenvalue. So there's the eigenvalue, there's the eigenvector. Let's just take a second on eigenvalue 0. From the point of view of eigenvalues, that's no special deal. We have an eigenvector. If the eigenvalue happened to be 0, that would mean that ax was 0x, in other words, 0. So where would we look first? What are the x's? What are the eigenvectors with eigenvalue 0? They're the guys in the null space. Ax equals 0. So if our matrix is singular, so let me write this down. If A is singular, then what does singular mean? It means that it takes some vector x into 0, some non-zero vector, that's why, will be the eigenvector, into 0, then lambda equals 0 is an eigenvalue. But we're interested in all eigenvalues now. Lambda equals 0 is not like so special anymore. Okay, so the question is, how do we find these x's and lambdas? And notice, we don't have an equation ax equal b anymore. I can't use elimination. I've got two unknowns, and in fact, they're multiplied together. Lambda and x are both unknowns here. So we need a good idea of how to find them. But before I do that, and that's where determinants will come in, can I just give you some matrices? Like, here you go. Take the matrix, a projection matrix. Okay, so suppose we have a plane, and our matrix P is what I've called A. Now I'm going to call it P for the moment, because I'm thinking, okay, let's look at a projection matrix. What are the eigenvalues of a projection matrix? So that's my question. What are the x's, the eigenvectors, and the lambdas, the eigenvalues, for, and now let me say, a projection matrix? My point is that before we get into determinants and formulas and all that stuff, let's take some matrices where we know what they do. We know that if we take a vector B, what this matrix does is it projects it down to PB. So is B an eigenvector in that picture? Is that vector B an eigenvector? No. So B is not an eigenvector because PB, its projection, is in a different direction. So now tell me, what vectors are eigenvectors of P? What vectors do get projected in the same direction that they start? So answer. Tell me some x's. In this picture, where could I start with a vector B or x, do its projection, and end up in the same direction? Well, that would happen if the vector was right in that plane already. If the vector x was, let the vector x, so x, any vector, any x in the plane will be an eigenvector. And what will happen when I multiply by P, when I project a vector x, I called it B here because this is our familiar picture, but now I'm going to say that B was no good for our purposes. I'm interested in a vector x that's actually in the plane, and I project it, and what do I get back? X, of course. Doesn't move. So any x in the plane is unchanged by P. And what's that telling me? That's telling me that x is an eigenvector, and it's also telling me what's the eigenvalue, which is, just compare it with that, the eigenvalue, the multiplier, is just 1. Good. So we have actually a whole plane of eigenvectors. Now I ask, are there any other eigenvectors? And I expect the answer to be yes, because I would like to get 3, if I'm in 3 dimensions, I would like to hope for 3 independent eigenvectors, 2 of them in the plane and 1 not in the plane. Okay, so this guy B that I drew there was not any good. What's the right eigenvector that's not in the plane? The good one is the one that's perpendicular to the plane. There's another good x, because what's the projection? So these are eigenvectors. Another guy here would be another eigenvector. But now here's another one. Any x that's perpendicular to the plane. What's px for that vector? What's the projection of this guy perpendicular to the plane? It is 0, of course. So there's the null space. Px and for those guys are 0, or 0x if we like, and the eigenvalue is 0. So my answer to the question is, what are the eigenvalues for a projection matrix? There they are, 1 and 0. Okay, we know projection matrices. We can write them down as that A transpose A inverse A transpose thing, but without doing that, from the picture, we can see what are the eigenvectors. Okay. Are there other matrices? Let me take a second example. How about a permutation matrix? What about the matrix? I'll call it A now. 0, 1, 1, 0. Can you tell me a vector x? See, we'll have a system soon enough. So I would like to just do these couple of examples just to see the picture before we let it all go into a system where that matrix isn't anything special, because it is special. And what vector could I multiply by and end up in the same direction? Can you spot an eigenvector for this guy? That's a matrix that permutes x1 and x2, right? It switches the two components of x. How could the vector with its x2, x1 with permuted turn out to be a multiple of x1, x2, the vector we start with? Can you tell me an eigenvector here for this guy? X equal. Actually, can you tell me one vector that has eigenvalue 1? So what vector would have eigenvalue 1? So that if I permute it, it doesn't change. That could be 1, 1. Thanks. 1, 1. Okay, take that vector 1, 1. That will be an eigenvector because if I do AX, I get 1, 1. So that's the eigenvalue is 1. Great. That's one eigenvalue. But I have here a 2 by 2 matrix, and I figure there's going to be a second eigenvalue and eigenvector. Now, what about that? What's a vector? Okay, maybe we can just guess it. A vector that actually this one that I'm thinking of is going to be a vector that has eigenvalue -1. That's going to be my other eigenvalue for this matrix. Notice a nice positive or not negative matrix, but an eigenvalue is going to come out negative. And can you spot the x that will work for that? So I want a vector when I multiply by A, which reverses the two components. I want the thing to come out minus the original. So what shall I send in that case? If I send in -1, 1, then when I apply A, I do that multiplication and I get 1, -1. So it reversed sign. So AX is minus x. Lambda is -1. So AX was x there, and AX is minus x here. Can I just mention, jump ahead and point out a special little fact about eigenvalues? N by n matrices will have n eigenvalues. And it's not let's suppose n is 3 or 4 or more. It's not so easy to find them. We'd have a 3rd degree or a 4th degree or an nth degree equation. But here's one nice fact. There's one pleasant fact, that the sum of the eigenvalues equals the sum down the diagonal. That's called the trace, and I put that in the lecture content specifically. So this is a neat fact, that the sum of the lambdas add up the lambdas, equals the sum. What would you like me to, how shall I write that down? What I want to say in words is the sum down the diagonal of A. Shall I write A11 plus A22 plus ANN? That's add up the diagonal entries. In this example, it's 0. In other words, once I found this eigenvalue of 1, I knew the other one had to be minus 1 in this 2 by 2 case, because in the 2 by 2 case, which is a good one to play with, the trace tells you right away what the other eigenvalue is. So if I tell you one eigenvalue, you could tell me the other one. We'll have that. We'll see that again. Okay. Now, I could give more examples, but maybe it's time to face the equation AX equal lambda x and figure how are we going to find x and lambda. Okay, so the question now is how to find eigenvalues and eigenvectors. How to solve AX equal lambda x when we've got two unknowns both in the equation. Okay, here's the trick. Simple idea. Bring this onto the same side. Rewrite. Bring this over as A minus lambda times the identity x equals 0, right? I have AX minus lambda x. So I brought that over and I've got 0 left on the right-hand side. Okay. I don't know lambda and I don't know x, but I do know something here. What I know is if I'm going to be able to solve this thing for some x that's not the 0 vector, that's a useless eigenvector, doesn't count. What I know now is that this matrix must be what? If I'm going to be able, if there is an x, I don't care if right now I don't know what it is. I'm going to find lambda first, actually. But if there is an x, it tells me that this matrix, this special combination, which is like the matrix A with lambda shifted by lambda I, that it has to be singular. This matrix must be singular, otherwise the only x would be the 0x and 0 interest. Okay, so this is singular. And what do I now know about singular matrices? Their determinant is 0. So from the fact that that has to be singular, I know that the determinant of A minus lambda I has to be 0. And that, now I've got x out of it. I've got an equation for lambda, the key equation. It's called the characteristic equation, or the eigenvalue equation. And that, in other words, I'm now in a position to find lambda first. So this is the idea will be to find lambda first. And actually, I won't find one lambda. I'll find n different lambdas. Well, n lambdas, maybe not n different ones. A lambda could be repeated. A repeated lambda is the source of all trouble in 1806. So let's hope for the moment that they're not repeated. They were different, right? 1 and minus 1 for that permutation. Okay, so, and after I found this lambda, can I just look ahead? How am I going to find x? after I have found this lambda, the lambda being this, one of the numbers that makes this matrix singular, then, of course, finding x is just by elimination, right? It's just, now I've got a singular matrix. I'm looking for the null space. We're experts at finding the null space. You know, you do elimination, you identify the pivot columns and so on, and give values to the free variables. Probably there will only be one free variable. We'll give it the value 1, like there, and we find the other variable. Okay, so let's... Finding x second will be a doable job. Let's look at the first job of finding lambda. Okay, can I take another example? And let's work that one out. Okay, so let me take the example, say, let me make it easy. 3, 3, 1, and 1. So I've made it easy. I made it 2 by 2. I made it symmetric. And I even made it constant down the diagonal. So so the more like special properties I stick into the matrix, the more special outcome I get for the eigenvalues. For example, this symmetric matrix, I know that it'll come out with real eigenvalues. The eigenvalues will turn out to be nice real numbers. And up in our previous example, that was a symmetric matrix. Yeah, actually, while we're at it, that was a symmetric matrix. Its eigenvalues were nice real numbers, 1 and minus 1. And do you notice anything about its eigenvectors? Anything particular about those two vectors, 1, 1 and minus 1, 1? They just happen to be? No, I can't say they just happen to be, because the whole point is that they had to be. What? What are they? They're perpendicular. The vector, if I see a vector 1, 1 and a minus 1, 1, my mind immediately takes that dot product. It's 0. Those vectors are perpendicular. That'll happen here too. Well, let's find the eigenvalues. Actually, my example's too easy. My example is too easy. Let me tell you in advance what's going to happen. May I? Or shall I do the determinant of a minus lambda and then point out at the end? Will you remind me after I found the eigenvalues to say why they were easy from the example we did? Okay, let's do the job here. Let's compute determinant of a minus lambda I. So that's a determinant. And what is this thing? It's the matrix A with lambda removed from the diagonal. So the diagonal matrix is shifted, and then I'm taking the determinant. Okay, so I multiply this out. So what is that determinant? You notice I didn't take lambda away from all the entries. It's lambda I, so it's lambda along the diagonal. So I get 3 minus lambda squared and then minus 1, right? And I want that to be 0. Well, I'm going to simplify it. And what will I get? So if I multiply this out, I get lambda squared minus 6 lambda plus what? Plus 8. And that I'm going to set to 0. And I'm going to solve it. So, and it's a quadratic equation. I can use factorization. I can use the quadratic formula. I'll get 2 lambdas. Before I do it, tell me, what's that number 6 that's showing up in this equation? It's a trace. That number 6 is 3 plus 3. And while we're at it, what's the number 8 that's showing up in this equation? It's the determinant. Our matrix has determinant 8. So in a 2 by 2 case, it's really nice. It's lambda squared minus the trace times lambda. The trace is the linear coefficient, plus the determinant, the constant term. Okay, so can we find the roots? I guess the easy way is to factor that as something times something. If we couldn't factor it, then we'd have to use the old b squared minus 4ac formula, but I think we can factor that into lambda minus what times lambda minus what? Can you do that factorization? 4 and 2? Lambda minus 4 times lambda minus 2. So the eigenvalues are 4 and 2. So the eigenvalues are one eigenvalue, lambda 1, let's say, is 4. Lambda 2, the other eigenvalue, is 2. The eigenvalues are 4 and 2. And then I can go for the eigenvectors. You see, I got the eigenvalues first. 4 and 2. Now for the eigenvectors. So what are the eigenvectors? They're these guys in the null space when I make the matrix singular by taking 4i or 2i away. So we got to do those separately. Let me find the eigenvector for 4 first. So I'll subtract 4, so a minus 4i is, so taking 4 away, we'll put minus 1s there. And what's the point about that matrix? If 4 is an eigenvalue, then a minus 4i had better be a what kind of matrix? Singular. If that matrix isn't singular, the 4 wasn't correct. But we're okay, that matrix is singular, and what's the x now? The x is in the null space. So what's the x1 that goes with the lambda 1? So this is, now I'm doing ax1 is lambda 1 x1. So I took a minus lambda 1i, that's this matrix, and now I'm looking for the x1 in its null space, and who is he? What's the vector x in the null space? Of course, it's 1, 1. So that's the eigenvector that goes with that eigenvalue. Now how about the eigenvector that goes with the other eigenvalue? Can I do that with erasing? I take a minus 2i. So now I take 2 away from the diagonal, and that leaves me with a 1 and a 1. So a minus 2i has again produced a singular matrix, as it had to. I'm looking for the null space of that guy. What vector is in its null space? Well, of course, a whole line of vectors. So when I say the eigenvector, I'm not speaking correctly. There's a whole line of eigenvectors, and I just want a basis. And for a line, I just want one vector. But there's some freedom in choosing that one, but choose a reasonable one. What's a vector in the null space of that? Well, the natural vector to pick as the eigenvector with lambda 2 is minus 1, 1. If I did elimination on that vector and set the free variable to be 1, I would get minus 1 and get that eigenvector. So do you see then that I've got eigenvector, eigenvalue, eigenvector, eigenvalue for this matrix, and now comes that thing that I wanted to be reminded of. What's the relation between that problem, and let me write just above what we found here, a equals 0, 1, 1, 0. That had eigenvalues 1 and minus 1, and eigenvectors 1, 1, and eigenvector minus 1, 1. And what do you notice? How is this matrix related to that matrix? How are those two matrices related? Well, one is just 3i more than the other one, right? I just took that matrix and I took this matrix and I added 3i. So my question is, what happened to the eigenvalues and what happened to the eigenvectors? That's like the question we keep asking now in this chapter. If I do something to the matrix, what happens or I know something about the matrix, what's the conclusion for its eigenvectors and eigenvalues? Because those eigenvalues and eigenvectors are going to tell us important information about the matrix. And here, what are we seeing? What's happening to these eigenvalues 1 and minus 1 when I add 3i? It just added 3 to the eigenvalues. I got 4 and 2. 3 more than 1 and minus 1. What happened to the eigenvectors? Nothing at all. 1, 1 is, and minus 1, 1 are still the eigenvectors. In other words, simple but useful observation. If I add 3i to a matrix, its eigenvectors don't change, and its eigenvalues are 3 bigger. Let's just see why. Let me keep all this on the same board. Suppose I have a matrix A, and AX equal lambda x. Now I add 3i to that matrix. Do you see what the eigenvalues and eigenvectors are or how they're coming out? If, so there's an if AX equals lambda x, then this other new matrix, I just have an AX, which is lambda x, and I have a 3x from the 3x. So it's just sitting there. Lambda plus 3x. So if this had eigenvalue lambda, this has eigenvalue lambda plus 3, and the x, the eigenvector, is the same x for both matrices. Okay. So that's great. Of course, it's special. We got the new matrix by adding 3i. Suppose I had added another matrix. Suppose I know the eigenvalues and eigenvectors of A. So this little board here is going to be not so great. Suppose I have a matrix A, and it has an eigenvector x with an eigenvalue lambda. And now I add on some other matrix. So what I'm asking you is, if you know the eigenvalues of A, and you know the eigenvalues of B, let me say, suppose B, so this is if, let me put an if here. If AX equals lambda x, fine, and B has eigenvalues, what shall we call them? Alpha 1 and alpha, or say alpha, I'll use alpha for the eigenvalues of B for no good reason. You see, what I'm going to ask is, how about A plus B? Let me give you what you might think first. Okay, if AX equals lambda x, and if B has an eigenvalue alpha, then am I allowed to say, what's the matter with this argument? It's wrong. What I'm going to write up is wrong. I'm going to say Bx is alpha x, add those up, and you get A plus Bx equals lambda plus alpha x. So you would think that if you knew the eigenvalues of A and you knew the eigenvalues of B, then if you added, you would know the eigenvalues of A plus B. But that's false. A plus B, well, when B was 3I, that worked great. But this is not so great. And what's the matter with that argument there? We have no reason to believe that X is also an eigenvector of B. B has some eigenvalues, but it's got some different eigenvectors. Normally, it's a different matrix. I don't know anything special. If I don't know anything special, then as far as I know, it's got some different eigenvector Y, and when I add, I get just rubbish. I mean, I can add, but I don't learn anything. So not so great is A plus B. Or A times B. Normally, the eigenvalues of A plus B or A times B are not eigenvalues of A plus eigenvalues of B. Eigenvalues are not like linear, and they don't multiply. Because eigenvectors are usually different, and there's just no way to find out what A plus B does to a vector. Okay, so that's like a caution. Don't, if B is a multiple of the identity, great. But if B is some general matrix, then for A plus B, you've got to solve the eigenvalue problem. Okay. Now I want to do another example that brings out another point about eigenvalues. Let me make this example a rotation matrix. Okay, so here's another example. So a rotation, I better call it Q. I often use Q for rotations, because those are the very special, very important examples of orthogonal matrices. Let me make it a 90-degree rotation. So that my matrix is going to be the one that rotates every vector by 90 degrees. So do you remember that matrix? It's the cosine of 90 degrees, which is 0, the sine of 90 degrees, which is 1, minus the sine of 90, the cosine of 90. So that matrix deserves the letter Q. It's an orthogonal matrix, very, very orthogonal matrix. Now I'm interested in its eigenvalues and eigenvectors. 2 by 2, it can't be that tough. We know that the eigenvalues add to 0. Actually, we know something already here. What's the sum of the two eigenvalues? Just tell me what I just said. 0, right? From that trace business. The sum of the eigenvalues is going to come out 0. And the product of the eigenvalues, did I tell you about the determinant being the product of the eigenvalues? No, but that's a good thing to know. We pointed out how that 8 appeared in the quadratic equation. So let me just say this. The trace is 0 plus 0, obviously. And that's the sum, that's lambda 1 plus lambda 2. Now, the other neat fact is that the determinant, what's the determinant of that matrix? 1. And that is lambda 1 times lambda 2. In our example, the one we worked out, the eigenvalues came out 4 and 2. Their product was 8. It had to be 8 because we factored into lambda minus 4 times lambda minus 2. That gave us the constant term 8, and that was the determinant. Okay. What I'm leading up to with this example is that something's going to go wrong. Something goes wrong for a rotation because what vector can come out parallel to itself after a rotation? If this matrix rotates every vector by 90 degrees, what could be an eigenvector? You see, we're going to have trouble. Eigenvectors are, well, our picture of eigenvectors, of coming out in the same direction that they went in, there won't be any. And with eigenvalues, we're going to have trouble. From these equations, let's see. Why am I expecting trouble? The first equation says that the eigenvalues add to 0. So there's a plus and a minus. But then the second equation says that the product is plus 1. And we're in trouble. But there's a way out. So let's do the usual stuff. Look at determinant of q minus lambda I. So I'll just follow the rules, take the determinant, subtract lambda from the diagonal where I had zeros. The rest is the same. The rest of q is just copied. Compute that determinant. Okay, so what does that determinant equal? Lambda squared minus 1 plus 1. What's up? There's my equation. My equation for the eigenvalues is lambda squared plus 1 equals 0. What are the eigenvalues, lambda 1 and lambda 2? They're I, whatever that is, and minus it. Right. Those are the right numbers. They add to 0, as the trace requires, and they multiply to 1, as the determinant requires. But they don't happen to be real numbers, even though the matrix was perfectly real. So this can happen. Complex numbers are going to have to enter 1806 at this moment. Boo. Right. All right. If I just choose good matrices that have real eigenvalues, we can postpone that evil day. But just so you see, so I'll try to do that. But it's out there. That a matrix, a perfectly real matrix, could give a perfectly innocent-looking quadratic thing, but the roots of that quadratic can be complex numbers. And of course, everybody knows that they're. What do you know about the complex numbers? So now, let's just spend one more minute on this bad possibility of complex numbers. We do know a little information about the two complex numbers. They're complex conjugates of each other. If lambda is an eigenvalue, then when I go, you remember what complex conjugates are? You switch the sign of the imaginary part. Well, this was only imaginary, had no real part. So we just switched its sign. So that eigenvalues come in pairs like that, but they're complex, a complex conjugate pair. And that can happen with a perfectly real matrix. And as a matter of fact, so that was like my point earlier, that if the matrix was symmetric, it wouldn't happen. So if we stick to matrices that are symmetric or like close to symmetric, then the eigenvalues will stay real. But if we move far away from symmetric, and that's as far as you can move, because that matrix is, how is Q transpose related to Q for that matrix? That matrix is anti-symmetric. Q transpose is minus Q. That's the very opposite of symmetry. When I flip across the diagonal, I reverse all the signs. Those are the guys that have pure imaginary eigenvalues. So they're the extreme case, and in between are matrices that are not symmetric or antisymmetric, but they have partly a symmetric part and an antisymmetric part. Okay, so I'm doing a bunch of examples here to show the possibilities. The good possibilities being perpendicular eigenvectors, real eigenvalues. The bad possibilities being complex eigenvalues. We could say that's bad. There's another even worse. I'm getting through the bad things here today. Then the next lecture can be like pure happiness. Okay. Here's one more bad thing that could happen. So again, I'll do it with an example. Suppose my matrix is, suppose I take this 3, 3, 1, and I change that guy to 0. What are the eigenvalues of that matrix? What are the eigenvectors? This is always our question. Of course, the next sections are going to show why. Why do we care? But for the moment, this lecture is introducing them, and let's just find them. Okay, what are the eigenvalues of that matrix? Let me tell you, at a glance, we could answer that question. Because the matrix is triangular. It's really useful to know, if you've got properties like a triangular matrix, it's very useful to know you can read the eigenvalues off. They're right on the diagonal. So the eigenvalue is 3 and also 3. 3 is a repeated eigenvalue. But let's see that happen. Let me do it right. The determinant of A minus lambda I, what I always have to do is this determinant. I take away lambda from the diagonal. I leave the rest. I compute the determinant, so I get a 3 minus lambda times a 3 minus lambda and nothing. So that's where the triangular part came in. Triangular part, the one thing we know about triangular matrices is the determinant is just the product down the diagonal. And in this case, it's this thing repeated. So lambda 1 is 1. Lambda 1 is 3, and lambda 2 is 3. That was easy. I mean, no, why should I be pessimistic about a matrix whose eigenvalues can be read off right away? The problem with this matrix is in the eigenvectors. So let's go to the eigenvectors. So how do I find the eigenvectors? I'm looking for a couple of eigenvectors. So I take the eigenvalue. What do I do? Now, you remember I solve A minus lambda I x equals 0? And what is A minus lambda I x? So take 3 away, and I get this matrix 0, 0, 0, 1, right? Times x is supposed to give me 0, right? That's my big equation for x. Now I'm looking for x, the eigenvector. So I took A minus lambda Ix, and what kind of a matrix am I supposed to have here? Singular, right? It's supposed to be singular. And then it's got some vectors, which it is. So it's got some vector x in the null space. And give me a basis for the null space for that guy. Tell me what's a vector x in the null space. So that'll be the eigenvector that goes with lambda 1 equals 3. The eigenvector is, so what's in the null space? 1, 0, is it? Great. Now, what's the other eigenvector? What's the eigenvector that goes with lambda 2? Well, lambda 2 is 3 again. So I've got the same thing again. Give me another vector. I want it to be independent. If If I'm going to write down an x2, I'm never going to let it be dependent on x1. I'm looking for independent eigenvectors, and what's the conclusion? There isn't one. This is a degenerate matrix. It's only got one line of eigenvectors instead of two. This possibility of a repeated eigenvalue opens this further possibility of a shortage of eigenvectors. And so there's no second independent eigenvector, x2. So it's a matrix, it's a 2 by 2 matrix, but with only one independent eigenvector. So that will be, those are the matrices that where eigenvectors don't give the complete story. Okay, my lecture on Monday will give the complete story for all the other matrices. Thanks. Have a good weekend. A real New England weekend.